ourselves for the new year, starting with Parabola, right? So then, without wasting too much time on trivia, let's get into the business straight away. So this time, we are going to talk of yet another moving point in a plane. And this moving point, as always, moves subject to a certain condition. Now, this one moving point has two other members belonging to a family. These two are stable members of the family. One is a fixed point and one is a fixed straight line. So, we are talking of a point P moving a fixed point S and a fixed line L. All belonging to the same plane, and the point moving in the plane commensurate with the following condition. From S, its distance is SP. From the fixed line, the distance of this moving point is PM. While the point P moves, both SP and PM vary. As the point P moves, both SP and PM vary. But then, they still subscribe to a common condition at all instants of the moving point. The condition is that SP, the ratio of its distance from the fixed point to its distance from the fixed line, is a constant. Such is the trajectory of the moving point P. Such is the trajectory of the moving point P. It moves, varying its distance from the fixed point, varying its distance from the fixed line, but maintaining a constant ratio of these two distances, right? Its distance from the fixed point varies, its distance from the fixed line varies, but the ratio of the two distances is preserved. Such is the conditionality that applies to the moving point, right? The path traced by this moving point subject to this condition is referred to as a conic. The path traced by this moving point keeping this condition intact is called a conic. Right? This constant is commonly referred to as E, the eccentricity of the conic. It's a property of the conic. Different conics will subscribe to different values of E, the eccentricity. Eccentricity, therefore, is a fundamental property of the conic. This fixed point S, since it's stable, it's given a name. It's called the focus of the conic section. This fixed line L is called the directrix of the conic section. Right? Now, let me know if I could wipe this off, right? So, three most fundamental things about the conic: the fixed point S, the fixed line L, and its property E, eccentricity E, right? Now, this is the fixed line L, which is the directrix of the conic, right? This is the focus S of the conic section, and this one line perpendicular to the directrix and passing through the focus. This is a line perpendicular to the directrix and passing through the focus is called the axis of the conic section, is called the axis of the conic section. A line passing through the focus and perpendicular to the directrix is called the axis of the conic section, right? The moving point P, let's say at a certain instant, is somewhere here, where its ratio of its distance from the fixed point S to fixed line L, SP by PM, is E, the eccentricity of the conic section, is E, the eccentricity of the conic section. Now, notice, not all points in the plane will subscribe to this condition, right? A certain bunch of points will subscribe to this condition, and when you populate these points and join these points, you end up producing a conic based on the value of E that is assigned to the conic. Now, realize something very simple, very ordinary. If P is this point, and I take a reflection of this point about the axis, say P prime. If I take a reflection of P about this point, call it P prime, right? P is a point on the conic section, is one of the points through which this conic passes, one of the points through which this conic passes, and P prime is the mirror image of P. Right? Then, if P prime is the mirror image of P, then you can very readily see out of congruence that SP is the same as S prime P, SP prime. SP is the same as SP prime, right? These two triangles are congruent, right? And P prime M prime is the same as PM. P prime M prime, P prime M prime is the same as PM. Yes or no? Yes. Right? Which means if SP by PM is E, then SP prime by P prime M prime is also E. Right? That means if P is a point on the conic section, then P prime will also be a point on the conic section. Yes or no? Right? Every point above the axis that belongs to the conic section will automatically produce a reflected point about the axis which also lies on the conic section. Yes or no? Right? So whatever you see of the conic section above the axis is exactly what you will see of the conic section below the axis. Right? Do you all understand this? Right? That means the portion of the conic section above the x-axis and the portion of the conic section below the x-axis are actually mirror images of each other about the axis, right? And therefore, can I not claim with comfort that the conic is indeed symmetric about the axis, right? Any conic section, no matter what value of E, is going to be symmetric about the axis, right? So which means a conic will always be symmetric about the axis, about its axis. Sounds fair? Right? An axis, like I defined, was just another line passing through the focus but perpendicular to the directrix. Now, say if there was, let's say this was the axis of the conic section, say this was the axis of the conic section, right? This was the focus of the conic section. Then no matter what, the conic is going to, whatever you see of the conic above the axis is going to be the conic below the axis. Say for example, the conic turns out to be like this above the axis, then below the axis the conic will be like this. Yes or no? Yes. Right? Now, and this is the focus of the conic. This is the focus of the conic. Now, for every conic, this is a certain chord that passes through the focus of the conic. This is a chord that passes through the focus of the conic. This is a chord of the conic which passes through the focus of the conic and will be referred to as the focal chord. Will be referred to as the focal chord. PQ will be a focal chord of the conic. Right? SP and SQ are referred to as segments of the focal chord or focal radii. SP and SQ are segments of the focal chord also referred to as focal radii. They are also referred to as focal radii, right? Now, of all the focal chords, there would be one focal chord that is perpendicular to the axis. This is a focal chord that is perpendicular to the axis. This is a focal chord P prime Q prime, which is perpendicular to the axis of the conic. P prime Q prime is a focal chord perpendicular to the conic, perpendicular to the axis, beg your pardon, and is referred to as latus rectum, LR, henceforth LR. Yeah, infinite focal chords. Because there could be infinite number of lines passing through as being chords of the conic section, infinite number of focal chords really. P prime Q prime is a special focal chord which is perpendicular to the axis, and that focal chord is referred to as the latus rectum LR. This length P prime Q prime actually is called the latus rectum. This length P prime Q prime is called the latus rectum of the conic, right? And very clearly, since P prime and Q prime, you know, they must be symmetric about the axis of the conic section. So SP prime must be the same as SQ prime. And this SP prime and SQ prime are equal, and both are equal to L. It's called the semi-latus rectum. It's called the semi-latus rectum. It's called a semi-latus rectum of the conic. Right? Now, we also define, so I'm beginning to just define some rudiments related to conics. So again, if this is a conic, part of a conic, and if I take a system of parallel chords, that means each of slope m is the slope of each of these, a system of parallel chords, m is the slope of each of these chords, and I collected the midpoints of all these chords. If I collected the midpoint of all these chords, m1, m2, m3, m, these are the midpoints of all these chords, a system of parallel chords, and I collect the midpoints of all these chords, system of parallel chords, and m1, m2, m3, mn, m are the midpoints of all these chords, and I join the midpoints of a system of parallel chords. If I join the midpoints of a system of parallel chords, join the midpoint of a system of parallel chords, the locus produced is a diameter of the conic, is a diameter of the conic, is a diameter of the conic. Right? Is a diameter of the conic. We will have different diameters. Does the circle not have different diameters? Isn't it? See, if you look at a circle is also a special conic. See, in a circle, you take any system of parallel chords and join the midpoints of this system. Will you not get a chord that passes through the center of the circle, which is a diameter? You take another system of parallel chords, you get another diameter. A diameter is not a fixed entity. Infinite number of diameters will exist. Yes or no? Yes. Right? Yes. So, see again, no, that's a relevant question. In case of, see, it depends on the conic. In a circle, it will remain the same, right? In a parabola, there is no defined length. There is no defined length. In ellipse and hyperbola, it will be different. The lengths will be different, right? So, in fact, that's the fundamental difference between a circle and other conic sections. A circle will have all diameters of the same length, whereas other conic sections will have diameters that are different for different. In fact, in a parabola, which I am going to take to today, you will find that there is no fixed length of the diameter. It's just that you can take infinite number of parallel chords, keep joining them, and it will keep extending. There is no length as such for a diameter in case of a parabola. But in case of an ellipse and a hyperbola, there would be lengths associated with diameters, right? So then we also have a diameter, and then again, like we had for circles, we have for other conic sections also a director circle. A director circle, that's the locus of points. I'm going to come to that in greater details, but for the time being, that's the locus of points such that tangents drawn from those points to the conic section are mutually perpendicular. That's the director circle. That's the director circle, right? Now, with this background intact, let's go ahead and look at a conic section. So, first of all, just to reiterate matters, this is a fixed line, the directrix. This is a fixed point, focus. Yes, and this is the axis. The axis of the conic section is also the axis of symmetry, symmetry of the conic section. Clear? This is a moving point P, and it moves in a manner that SP by PM is a constant. SP by PM is a constant E, and this E is referred to as the eccentricity of the conic section. Now, for E equal to 1, the path traced, P traces what's called a parabola. P traces a path called parabola. E greater than 0 but less than 1, then the path traced is an ellipse. E greater than 1, the path traced is a hyperbola. So these are three fundamental varieties of conic sections: E lying between 0 and 1, ellipse; E equal to 1, parabola; E greater than 1, Hyperbola E equal to 0 is a circle which we have already read, right? Is a circle, is a circle. Now, now can I wipe this off? We are going to focus today on conic sections for which E is 1, that means SP is PM. E is 1, that means SP is PM. That means we will talk of points which move in a manner that their distances from a fixed point at any given instant will be equal to their distances from a fixed line, and the path traced is going to be referred to as a parabola. So we'll take attention to a conic section of this variety today, right? I'll come to that. You might want to realize it yourself in a little while from now, but for the time being, let me move on and give you an opportunity to imagine why it's going to. Once I do a little more of parabola, you'll yourself realize what this E means, right? Clear? Now, so focus S, point P, moving point P, such that SP is PM. SP is PM. So that brings us to the definition of a parabola. Definition of a parabola. SP is PM, SP by PM is 1, right? Bless you. Let me call this Z. Now, I know its property, I know the directrix, I know physically the location of the focus, I know where the axis is, everything. But I want an algebraic description of this point, right? I need an algebraic description of this point. Now, to get an algebraic description, that means one that would connect the x and the y coordinates of the moving point. That's going to be the algebraic description. Now, for that, I would need to define my coordinate axis. And it's my choice, my prerogative to define and design my own coordinate axis that will bring convenience of operation to me, right? Now, one convenient choice of coordinate axis could be the following. But even before I talk about the coordinate axis, one thing, any point in the plane such that its distance from the fixed point S is the same as its distance from the fixed line L will be part of the parabola, will belong to the parabolic trajectory. Clear? Now, if I took the midpoint of SZ, call it A, right? If A is the midpoint of SZ, then do you realize that AS, its distance from S, is the same as its distance from the directrix AZ? Therefore, A must lie on the parabola. A must lie on the parabola. A is a point on the parabola. A therefore is a point on the parabola. And this point A is called the vertex of the parabola. This point A is called the vertex of the parabola. Because any point whose distance from the focus is the same as its distance from the directrix is a point on the parabola. If A is the midpoint of SZ, then AS is AZ. Does it not subscribe to this condition? SP by PM is 1. AS by AZ is 1, isn't it? Right? So it must be a point on the parabola. Any point such that its distance from the focus is equal to its distance from the directrix must lie on the parabola. Right? This point A that lies on the axis and on the parabola, not every point on the axis will be a point on the parabola, right? But this one point, this is the only point that lies on the axis of the parabola, is also a point on the parabola. This point is referred to as the vertex of the parabola. This point is referred to as the vertex of the parabola. Yes or no? Right? Now, one more simple observation. see, if I move to the left of A, look at this line. This is a line around x equal to A. This is a line around A. But if I look at any point to the left of A in the plane, any point to the left of A, let's say this is a line parallel to the directrix, and I look at any point to the left of this line parallel to the directrix, then do you realize that it cannot be a point, no point here will ever lie on the parabola, because I am increasing the distance from the focus, I am decreasing the distance from the directrix, so it's not possible. So no point to the left of A in this case for this configuration will ever lie on the parabola. That means the entire parabola will lie only to the right of A in the plane. You got me? Now okay, A therefore is also a point on the parabola, the vertex of the parabola, right? I can choose to call A the origin of coordinates. So now, since I want to describe P algebraically, I would want to know what my origin of coordinates is, what my x-axis is, what my y-axis is, right? And therefore, in line with that, in tune with that, I say, all right, the vertex of the parabola I am going to choose as the origin of coordinates. Okay, so this A is chosen as the origin of coordinates. Let me choose A as the origin of coordinates. Right, and might as well choose the axis of the parabola as the x-axis. Why not, right? We might as well choose the axis of the parabola as the x-axis, right? And a line passing through A and perpendicular to the x-axis will therefore by default be the y-axis, How about it? Right? Now with this description of our coordinate system and the origin, we are geared to give the description P a form, right? The point P, moving point P, now has coordinates x comma y, different for different instants, right? And A is the midpoint, right? A is the midpoint. Realize that the distance between S and the directrix is a property of the parabola, will be a property, because you know this will be fixed for the parabola. Fixed directrix, fixed focus, so SZ will be a property. SZ will be a property of the parabola. So might as well call this SZ as 2A, which is a fundamental property of the parabola, for a given parabola, right? Different parabolas will have different values of SZ, right? Now, very clearly then, AS and AZ both will be A. AS and AZ both will be A. So the coordinates of S, if this is A units, coordinates of S will be A0, and coordinates of Z would be minus A0. Right? This is a line parallel to the y-axis, and therefore its equation is going to be x equal to minus A for all points on this line, the equation of this line, the equation of the directrix, right? Which means x plus A equal to 0 is the equation of the directrix. X plus A is the equation of the directrix in this case, right? Make sense? Now, I want to connect the x and y coordinates of the moving point to get the equation of the trajectory, equation of the parabola, and that's going to be the standard equation of the parabola. All right. SP is PM, so SP squared is going to be PM squared. If SP is PM, then SP squared is going to be PM squared. What is SP squared? SP squared is x minus A whole squared plus y minus 0 whole squared. Now PM, realize that this length is x, this length is x, and this length is A units, right? This length is A units. So this length is going to be x plus A. PM is going to be x plus A, right? So this is going to be x plus A whole square right? Which means y squared is going to be x plus a whole squared minus x minus a whole squared. So I get y squared equal to 4ax. So the moving point P would have variable coordinates x and y, always satisfying this condition, always commensurate with this requirement. Yes or no? Right? Now notice. So this then is the standard equation of a parabola. This then is the standard equation of a parabola. Now notice that in this equation, y squared equal to 4ax, if x comma y satisfies this equation, if x comma y satisfies this equation, then x comma minus y will also satisfy this equation. Yes or no? If x comma y satisfies this equation, x comma minus y will also satisfy this equation. But x comma y, if that's a point here, then x comma minus y will be its mirror image about the axis. Yes or no? Which is only a quick check about the axis of symmetry being the same, right? Being the axis itself, being the axis of the parabola. So x comma y being a point, x comma minus y will also be a point on the parabola, right? Now the physicality is that the focus will always lie on the axis, right? And the vertex would always be halfway between the directrix and the focus, right? In this case, the conic section will exist only in that region from the vertex away from the directrix towards the focus. Away from the directrix towards the focus is where the graph will exist, right? Now, if I have to trace this, this is the y-axis, this is the directrix, x equal to minus a or x plus a equal to 0, that's the directrix. The vertex in this case lies in the origin, and the x-axis is also the axis. Of the parabola. The x-axis is also the axis by our definition, right? You have a question? No, give me some opportunity. I will vary all those things to the extent you can't imagine, but let me build it up from ground up, right? So y squared equal to 4ax, right? Symmetric about the axis, and you realize that as the numerical value of x increases, y increases, numerical value of y increases, right? And therefore, and symmetric about the axis, this being the vertex, as x increases, y increases numerically, and symmetry about the axis would produce a shape of this kind, where A0 is the focus of the parabola. A0 is the focus of the parabola. Clear? Right? So far so good, right? Now, we will learn shortly that at the origin, so this is a rough shape of the parabola. This is the rough shape of a standard parabola, y squared equal to 4ax. This will be the latest rectum. This will be the latest rectum of the parabola, PQ. A focal chord perpendicular to the axis will be the latest rectum of the parabola, right? So PQ is the latest rectum. Now, if I want to find the coordinates of P, see, for P, what is x? X is a, isn't it? For P, x is a, right? Now, if you plug in x as a, then you get, if you plug in x as a, P being a point, then y squared would be 4a squared, y would be plus minus 2a, right? So P would be A comma 2A plus 2A, and Q would be A comma minus 2A. Right? PQ then will be the latest rectum, which will be 4A, as you can see. This length is 2A units, this Y is also 2A units. So the latest rectum LR, which is PQ, is 4A. 4A. Semi-latest rectum is 2A. Semi-latest rectum is 2A, which means the distance between the focus and the directrix is the semi-latest rectum. Distance between the focus and the directrix is the semi-latest rectum, 2A. A property. A property. Focus and the directrix. Between the focus and the directrix is 2A, the semi-latest rectum, right? Now, can I wipe this off? Now, any point on this parabola, this is the parabola, standard parabola, symmetric about the axis, x-axis. The x-axis is the axis of symmetry of this parabola, SA0. Y square equal to 4AX. Any point on this standard parabola, P, will satisfy this condition, right? Will satisfy this condition. Any point P on the parabola will satisfy this condition. Y square equal to 4AX, where 4A is a property, the latest rectum. 4A is a property which is the latest rectum of the parabola. Now, any point on this parabola could have been selected. See, this is a representation in which x and y are present in the same equation. We could have a parametric representation of points on the parabola, which means any point on the parabola could have been selected as x equal to 80 squared, y is 280. Check this out. If I did that, then what is 4AX? 4AX, as you can see, is 4A squared t squared. What is y squared? Y squared is 4A squared t squared. So y squared turns out to be 4AX if x is of the form 80 squared, y is of the form 280. If x is of the form 80 squared, y is of the form 280, then it will always satisfy this condition, yes or no? Yes, if x is 80 squared, y is 280, it will always satisfy this condition. Therefore, any point on the parabola could be represented not just by x and y in Cartesian, but could have been represented parametrically as x is 80 squared, y is 280. Any point on the parabola could have been represented as x is 80 squared, y is 280. Where t is a parameter, where t is a parameter. Different points on the parabola will subscribe to different values of t, will subscribe to different values of t. So if I call this point t, then its coordinates would be 80 squared comma 280. If there is a point I call that as t1, then its coordinates would be 81 squared comma 2a t1, and so on and so forth. So t is a parameter. Any point on the parabola could have been written as x is 80 squared, y is 280. T would be different for different points on the parabola. This is called a parametric representation of a point on a standard parabola. Parametric representation of points on a parabola. Any xy could have been written as 80 squared comma 280 on the parabola, because if it's of this form, then it will satisfy this condition and will therefore lie on the parabola. Right? Sounds good? Now, more than anything else, what I want you to take notice of is the physicality of this equation. The physicality is important to understand, right? Y squared equal to 4AX actually means the following, you know. This was the standard parabola, x comma y right? This is the vertex V, this is the vertex V, this is the focus S A0. In fact, very shortly we learned that this is a tangent to the parabola at the vertex. We learned that this line that we have drawn passing through the vertex, this is a line passing through the vertex and parallel to the directrix. This is a directrix. This is a line passing through the vertex and parallel to the, this is a line passing through the vertex and parallel to the directrix. We learned is actually a tangent at the vertex, is a tangent at the vertex, tangent drawn to the parabola at the vertex. We'll learn more about it, but for the time being just take it from me. This is the tangent drawn to the parabola at the vertex, right? Now let's interpret this result physically, y square equal to 4ax. Let's interpret this result physically, where what is 4a? 4a is a property of the parabola, which is the lattice rectum, right? Now do you realize that this y means what? This is the axis. In this case, for convenience, we called it the x-axis, but it could have been anything else. The axis could have been some Lx plus My plus n equal to 0, right? In which case, what would not change? See, what would this y squared then mean? This y squared would then mean square of the distance of any point from the axis. Y squared would actually mean square of square of the distance of any point from the axis, which may or may not be the x-axis. The axis of symmetry could have been defined anyway. Our coordinate system could have been defined differently, in which case the axis may not turn out to be the x-axis, right? It could be some line Lx plus My plus n equal to 0, but then this y squared would be square of the distance from the axis of the parabola, which is the axis of symmetry. So physically this is square of the distance from the axis, square of the distance from the axis. Axis means axis of symmetry is equal to 4a. What is 4a? Lattice rectum into x. X is this distance. Do you realize that? X is this distance. So equal to lattice rectum into its distance from the tangent drawn at the vertex. Into its distance, lattice rectum into distance of P from the tangent drawn at the vertex. Y squared actually means square of the distance from the axis. Square of the distance from the axis is lattice rectum into distance of P from the tangent drawn at the vertex. Tangent drawn at the vertex. That's the physicality that I want you to bear in mind and flush with. Okay. This equation could assume different forms, but this property of the parabola will remain intact irrespective of where we choose our coordinate system, how we choose our x and the y axis, where we choose our origin, here or in Japan. The fact will not change. What fact? That square of the distance of any point from the axis will be lattice rectum into its distance from the tangent drawn at the vertex. Right, so this is very cardinal and almost biblical. Okay, so take notice of this. Now so every time I write an equation or something, in most cases there will be something physical, something very geometrical about that equation. That's the fact that you must take very special notice of, so that in the event of a generalized situation, you not the best one for New Year's. So let's go ahead and obtain some more important and relevant facts related to a parabola. Now a standard parabola say y squared equal to 4ax so this is a parabola essentially is a conic section that doesn't have a center. It's a conic section that doesn't have a center. Unlike other conic sections, the ellipse, the hyperbola, circle, all will have centers. Those are central conics. The parabola belongs to a variety which is a conic section without a center, no center of this conic. Okay. However, it still has an inside and an outside. This region of the parabola is called the inside of the parabola, right? And the region out of this is called the outside. This is outside of the parabola, right? Now, like we've always done, we define an expression S. S is only an expression. This is defined as y squared minus 4ax is just an expression. For any point xy in the plane, I can find the value of S, right?
How do you distinguish between inside and outside, because it will be open, right?
So all points here, you know, it will go up. This will all be inside, and above this curve will be outside, or below this curve will be outside. This would be outside. That's how you distinguish.
That the area containing the focus is the inside.
The region.
The region containing the.
No, that's actually, you know, again the region containing the focus. You can say, well, this region also contains the focus, so this can't be an outside. That's not the way you want to define. So in any case, we define an expression S as y squared minus 4as x, right? If I take any point xy, say, then I can find the value of S for this point P. By plugging in x of this point, y of this point, I can find the value of the expression S for every point in the plane. For some points in the plane, for some xy's in the plane, S will become 0. Those are the points that lie on the parabola, right? For other points, S will either be greater than 0 or S will be less than 0, right? We define an expression S1 for any point x1, y1. For any point x1, y1, we define S1, the value S1 as y1 squared minus 4a x1. If for a x1, y1, this becomes 0, this value turns out to be 0, then that point lies on the parabola y squared equal to 4ax. For other points, S1 will either be greater than 0 or S1 will be less than 0, right? Now, say there is a point P x1, y1 outside. There is a point P x1, y1 outside the parabola, right? Its projection, call it Q, would be x1 comma 0, right? And its intersection with the parabola R would be some x1 comma y, x1 comma y. Yes or no? Right, Siddhant? But this x1 comma y lies on the parabola, so will satisfy the equation of the parabola. So can I say y1 squared is 4y squared, that means this y plugged into this, y squared is 4ax1. Can I say this? Right? Now, if P is a point outside the parabola, can I not say mod of y1 will be greater than mod of y? Can I say that? Mod of y1 will be greater than mod of y if P is outside the parabola, right? So if P is outside the parabola, then mod of y1 will be greater than mod of y, right? And if P is inside, then mod of y1 would be less than mod of y, right? That's how you distinguish between points inside and outside, right? That means if I square both sides, I get y1 squared greater than y squared. But what is y squared? Y squared is 4ax1. Right? Which means y1 squared minus 4ax1 must be greater than 0. If x1, y1 is a point outside the parabola, then y1 squared minus 4ax1 is greater than 0. That means s1 greater than 0 for points outside the parabola. S1, the value of s at x1, y1 will be greater than 0 for all x1, y1 that lie outside the parabola, right? And for this, if you square this, you will end up getting s1 less than 0 for all points that lie inside the parabola. Because see, just the direction of the inequality will change, everything remains the same, you will get less than 0. So s1 less than 0 for all x1, y1 that lie inside the parabola will be greater than 0 for all points that lie outside the parabola. S1 will be equal to 0 for all x1, y1 that lie on the parabola. Right? Can I wipe this off? Is this understood by all? Now, see some noteworthy facts. Y squared equal to 4ax. Okay. This was a parabola whose description had a square term and a linear term. Right? And when I equated the square term to 0, y squared equal to 0, I got y equal to 0. This is the square term equated to 0. And I got y equal to 0, which was the axis of symmetry. Yes or no? If you equate the square term to 0, you get the axis of symmetry. Isn't it? Y equal to 0, the x-axis is the axis of symmetry in this case, right? Now, when you equate both to 0, y squared equal to 0 and the linear term to 0, y squared is 0, linear term equal to 0, you get y equal to 0, x equal to 0, you get the vertex of the parabola. Yes or no? Now in this case, for a parabola of this kind, see, for any xy on the parabola, if A is positive, then for xy to be a point on the parabola, x would have to be greater than or equal to 0. Because if x was negative, then y squared will turn out to be negative, it will then not be a point on the parabola, because y squared cannot be negative for any xy on the parabola, right? So if xy satisfies this condition, then x would have to be greater than or equal to 0. Therefore, the parabola lies only to the right of the y-axis. X has to be greater than or equal to 0. This is the axis of symmetry obtained by equating the square term to 0. Equating both to 0, you get the vertex, which is 0, 0. And now, if this is the axis of symmetry and this is the vertex, the parabola could have opened rightwards or could have opened leftwards, right? It could have, if this is the axis of symmetry, it could either have been like this or it could have been like this. But why is it like this? Because x cannot be negative here. If x were to be negative, y squared would be negative, will not give you real values of y. Got me now? However, if we had, say, y squared equal to minus 4ax, Now this also is a parabola whose axis of symmetry is obtained by y squared equal to 0 or y equal to 0 is the axis of symmetry of the parabola, right? Whose vertex is obtained by plugging in y squared equal to 0 and x equal to 0, the right hand side equal to 0, right? So the vertex is 0 0 and the axis is y equal to 0 for this parabola, right? So the axis is the same as this, the vertex is the same as this, but now this comes with a minus sign. Look, for this parabola the x axis is the axis, right? The vertex is 0 0, this is the axis of symmetry. Now the parabola in this case, for y squared to be y to be defined, x would have to be less than or equal to 0, isn't it? In this parabola x would have to be less than or equal to 0. That means this parabola will exist only to the left of the y axis, and if this is the axis of symmetry and this is the vertex, the parabola must be designated such, right? So this is a parabola that opens leftwards. Clear? So do you realize what the minus sign does here? No? Put the square term equal to 0, you get the axis of the parabola, right? Put both equal to 0, you get the vertex of the parabola 0 0. This is the vertex, this is the axis of symmetry, right? Now if this is the axis of symmetry, the parabola could open this way or could open this way, but in this case realize x would have to be less than or equal to 0. Why? Because otherwise if x was greater than 0, this will become a negative number. Y squared equal to negative will not give me real values of y, but any point xy on the parabola would have real values of y, right? When can that happen? Only if x is less than or equal to 0. That means any point on the parabola would have negative values of x only. Therefore it has to open this way. Am I confusing you? No? Now give me some time, that's what I'm coming to. I'll give you all generalizations, just give me a few minutes.
So in this case, you will consider latest rectum to be negative.
No, latest rectum is still 4a. Latest rectum is a length which will still be 4a, right? In both cases the tangent at the vertex is the y-axis, obtained by putting the linear term equal to 0. 4ax equal to 0 will give you x equal to 0, which will give you the tangent drawn at the vertex of the parabola, right? Now suppose I had something like this. Instead of y squared equal to 4ax, see this y squared equal to 4ax had axis of symmetry AOS, x equal to 0 was tangent at vertex, and 0 0, the intersection of the axis of symmetry with the tangent at the vertex will always give you the vertex, will be the vertex. The intersection of the axis of symmetry with the tangent at the vertex will always give you the vertex, right? So in this case 0 0 is the vertex, right? Now let me revise this a little bit, right? Say y minus y1 whole square is 4a into x minus x1. Now this again is a parabola. This is the square term, this is the linear term, 4a is the latest rectum. This is a parabola whose axis of symmetry AOS obtained by plugging the square term equal to 0. That means y minus y1 equal to 0. That means y equal to y1 is the revised axis of symmetry. Y equal to y1 is the revised axis of symmetry. The vertex of this parabola obtained by plugging in y minus y1 whole square equal to 0 and x minus x1 equal to 0 will give me x equal to x1 and y equal to y1. That's the vertex of this parabola. That's the vertex of this parabola. Which means now, look, this is the x-axis, This is the y-axis. And the axis of symmetry is y equal to y1. This is the axis of symmetry of the parabola, right? Y equal to y1 is the axis of symmetry of the parabola. And the vertex of the parabola is x1 comma y1. x1 comma y1 is the vertex of the parabola. Right? Yes or no? Now, if A is positive, then do you realize that x would have to be greater than or equal to x1 for any point on the parabola? X minus x1 should not be negative, because this is square of a number, can't be negative. So x minus x1 has to be greater than or equal to 0. That means the parabola would exist only to the right of x equal to x1. And if this is the axis of symmetry, the parabola would be designated such. This would be the looks of the parabola, yes or no? Yes, sir. The focus will lie somewhere here. Will lie somewhere here, and would be, since the latest rectum is 4a, the focus is always a units away from the vertex, isn't it? When the vertex was 0, 0, the focus was a0. The focus lies on the axis a units away from the vertex. So a units away from the vertex means the focus is going to be x1 plus a comma y1. Yes or no? See, in the parabola y squared equal to 4ax, this was the vertex 0, 0. This was the focus a0. What was the physicality about this notion? That the focus was a units away from the vertex, not the origin, from the vertex. The physicality is a units away from the vertex on the axis of symmetry. So if this is the vertex, this is the axis of symmetry, then the focus would be a units away from the vertex on the axis of symmetry. So if this is x1, this would be x1 plus a comma y1. Yes or no? And the directrix would be perpendicular to the axis of symmetry. This is the axis of symmetry. The directrix would be perpendicular to the axis of symmetry and would be a units to the left of the vertex. Would be a units to the left of the vertex. Therefore, if this is x1, do you realize that this would have x coordinate x1 minus a comma y1 would be the coordinates of this point? Right? A units to the left of this would be x1 minus a. Right? So the equation of the directrix would be x equal to x1 minus a would be the equation of the directrix of this parabola. Yes or no? Now, instead of this, so far so good, right? All of you understand this? Got me? Instead, suppose I had y minus y1 whole square equal to minus 4a into x minus x1. Now, in this parabola, realize again the axis of symmetry would be y equal to y1 would be the axis of symmetry, AOS. The vertex will still be x1 comma y1 would be the vertex. The latest rectum will still be 4a units, but this has to be non-negative. So x would have to be less than or equal to x1. X would have to be less than or equal to x1 for any xy on the parabola. For any xy on the parabola, x minus x1 would have to be negative. No? Got me, no? In order that the right hand side is non-negative, right? So, which means now this parabola y equal to y1 is the axis of symmetry. The vertex is x1 comma y1, right? Any point on the parabola would have to be x less than or equal to x1, and if this is the axis of symmetry, then for x to be less than or equal to x1, for all points p on the parabola, x would have to be less than or equal to x1, therefore the parabola should be to the left of the vertex. This would be the state of the parabola. Where would the focus be? Now for this parabola, the focus S would be x1 minus a, right? A units away from the vertex. So x1 minus a comma y1 would be the focus of this parabola. Clear? And the directrix of the parabola, this is the directrix, would be x equal to, this is x1 plus a. A units away from the vertex would be the directrix. So x would be x1 plus a would be the directrix of this parabola. Yes or no? So this form or this form, what does it give me? It gives me, no, not yet general, hardly close to general. This gives me the equation of a parabola. If the square term involves y, it gives me the equation of a parabola whose axis is parallel to the y-axis, x-axis, whose axis is parallel to the x-axis. Yes or no? This gives me a parabola whose axis is parallel to the x-axis. Axis would be y equal to y1, which is an axis parallel to the x-axis. Parabola, this represents the bunch of parabolas whose axis is parallel to x-axis. Right? Now, in a very general sense, see, when I write y minus y1 whole square is a constant, 4a is a constant, it could either be right plus 4a or minus 4a, some constant into x minus x1, right? What did it give me? It gave me a parabola whose axis is parallel to the x-axis, right? And if you take notice of this, x1, y1 are fixed numbers. The vertex of the parabola, that's a fixed number. Do you realize that this eventually will reduce to x equal to a quadratic in y? I mean, if you collect all terms, there is a y squared term minus 2y y1, right? And then constant into x1 would be some constant brought on the left hand side, right? So do you realize that this would be of the form some ay squared plus by plus c, x equal to ay squared plus by plus c, x equal to a quadratic in y. Do you realize it will reduce to this? Right now? So every time x is a quadratic in y, then it will give me a parabola whose axis is parallel to the x-axis, whose axis is parallel to the x-axis. X equal to a quadratic in y will give me a parabola whose axis is parallel to the x-axis. Clear? Which means, say if someone gave me x equal to 3y squared minus 4y plus 1 and said trace this parabola, which is x is a quadratic in y. If I had to trace this, what I would do is the following. Can I wipe this off? Three into y squared minus 2 into 2 by 3. See, I take 3 common from this, so 4 by 3. So 2 into 2 by 3 y plus 4 by 9 plus 1 minus 4 by 3. You realize what I have done here? Square, completed a square. See, this 1 was already there, and this 3 into 4 by 9, that is 4 by 3, I brought from outside, so I balanced it here with a minus 4 by 3, right? Which is like 3 into y minus 2 by 3 whole squared minus 1/3, right? Which then I could write as y minus 2 by 3 whole squared. 3 into y minus 2 by 3 whole squared is x plus 1/3, right? Or y minus 2 by 3 whole squared is 1/3 into x plus 1/3, right? Which is like 4a. A is 1 by 12 here. I multiply and divide by 4. So 4 into 1 by 12, x plus 1/3. Yes or no? Now, the axis of symmetry would be y equal to 2 by 3. If you put the square term equal to 0, then y equal to 2 by 3 would be the axis of symmetry. This always will be a parabola whose axis of symmetry will be parallel to the x-axis, right? So, axis of symmetry is x equal to 2 by 3, y equal to 2 by 3 is the axis of symmetry of the parabola, right? What's the vertex of the parabola? Minus 1 by 3 comma 2 by 3. The vertex would be minus 1 by 3 comma 2 by 3 would be the vertex of the parabola. Now, the parabola is symmetric about the axis, right? It could, with this the vertex, it could either be like this, open to the right, or it could open to the left. Now, in this case, this has to be a non-negative number. So, x would have to be greater than minus 1/3, greater than or equal to minus 1/3. So, then it has to open to the right, so that x is greater than or equal to minus 1/3. So, this will be a parabola stationed this way. No? Right? The focus would be S somewhere here inside the parabola, right? And it would be a units away from the vertex. A is 1 by 12 for this, right? So, focus would be minus 1/3 plus 1 by 12 comma 2 by 3. The directrix 1 by 12 units away from the vertex in this direction, right? So, x would be minus 1/3 minus 1 by 12 would be the directrix of the parabola, right? Right? That is still not general. These are only special parabolas where the axis is parallel to the x-axis in this case, or now I'll look at axis parallel to the y-axis, but the axis could be inclined to the x and the y-axis. That will be the most general thing. But then let me build it up slowly for you. Okay? But so far so good, right? All's good so far. Make sense now? Suppose, yeah, please ask. All's fine? Can I wipe this off? So, x equal to a quadratic in y will always give me a parabola whose axis is parallel to the x-axis. And you complete a square, and this is how you find the vertex, the axis of symmetry, the latest rectum. What's the latest rectum for this parabola? 1/3. 1 by 3? No, 1 by 3 is the latest rectum. A is 1 by 12, right? If it was minus 4 into this, then the parabola would have opened this way, leftwards, right? Suppose I had x squared equal to 4ay, a square term and a linear term, right? This will be the parabola. This will be a parabola. If you put the square term equal to 0, you get the axis of symmetry, right? So, x squared equal to 0 will give me the axis of the parabola. That means x equal to 0 will give me the axis of parabola, which is the y-axis, right? If you put both equal to 0, x squared equal to 0 and the linear term equal to 0, you get 0, 0. The intersection of this will give me the vertex of the parabola, right? The latest rectum of the parabola will be 4a, right? So, now this is a parabola whose axis is the y-axis. Y-axis is the axis of this parabola, right? The vertex is 0, 0. Now, if this is the axis of symmetry, the parabola could either open this way or it could open this way, upward or downward. If this is the axis of symmetry, the y-axis, it could either open up like this or it could open down like this, right? Now, in this case, do you realize that y has to be greater than or equal to 0? Because this is non-negative, this has to be non-negative. So, y would have to be greater than or equal to 0. Therefore, the parabola has to open upwards. Y of any point on the parabola would have to be greater than or equal to 0. So, the parabola would have to open upwards. Right? The focus of the parabola would be a units away from the vertex on the axis of symmetry, right? So, if this is the vertex, then 0 comma a, this would be a units away, right? The directrix would be perpendicular to the axis and a units below this. So, this would be y equal to minus a, would be the directrix of this parabola. Right? Simple. Suppose you had x squared equal to minus 4ay. Again, x equal to 0, x squared equal to 0 or x equal to 0 will still be the axis of symmetry of the parabola, right? X squared equal to 0 and linear term equal to 0, that is 0, 0 will still give me the vertex of the parabola, right? Yes or no? So, then the y-axis, y equal to 0, x equal to 0, that means the y-axis is the axis of symmetry of the parabola, right? Yx, right? In this case, do you realize that if x squared is minus 4ay, y would have to be less than or equal to 0, right? And if this is the axis of symmetry, for y less than or equal to 0, the parabola ought to be opening this way, downwards. X squared equal to minus 4ay ought to be opening downwards. What's the latest rectum of the parabola? 4a. So, then where is the focus? A units below this, so 0 comma minus a. What's the directrix? Y equal to plus a. So, one thing, do you see that this parabola along with its content is really the mirror image of this parabola along with its contents. X squared equal to 4ay and x squared equal to minus 4ay are actually mirror images of each other about the x-axis, isn't it? Now, see, if I had x minus x1 whole square equal to 4a into y minus y1. This is a parabola whose axis of symmetry is given by putting the square term equal to 0. That means x equal to x1 will be the axis of symmetry. If you put the square term equal to 0, you get x equal to x1. That's the axis of symmetry. So, this is the line x equal to x1, right? The axis lies here. Where is the vertex of this parabola? Put this equal to 0 and this equal to 0, then the x and y obtained are x1 comma y1. That's the vertex. So, always the vertex will always be on the axis of symmetry, right? So, the vertex V is x1 comma y1, right? Now y has to be greater than or equal to y1. Because this is non-negative, this has to be non-negative. So, y would have to be greater than or equal to y1 for all x, for points on the parabola. Y would have to be greater than or equal to y1. And if this is the axis of symmetry, the parabola would be disposed like this, right? Yes or no? Right? The focus of the parabola would be here. A units away from the vertex means x1 comma y1 plus a, right? This would be the directrix, y equal to y1 minus a. right? If instead of x minus x1 whole squared equal to 4a into y minus y1, if you had minus 4a into y minus y1, then y would have had to be less than or equal to y1, and then the parabola would have opened downwards, with this being the vertex, same axis of symmetry, right? Now, what does it produce? It produces a parabola whose axis of symmetry is parallel to the y-axis it produces a parabola whose axis of symmetry is parallel to the y-axis, right? But what is it actually? See, if you divide by 4a and put all terms in perspective here, you get y equal to some ax squared plus bx plus c kind of a thing, isn't it? Which is a quadratic in x. So y equal to a quadratic in x will always produce a parabola whose axis is parallel to the y-axis. X equal to a quadratic in y will produce a parabola whose axis is parallel to the x-axis. Clear? Yes or no? However, can I wipe this off? In a very general sense, most general sense, right, where we had predefined coordinate axis, then you don't have the choice of calling the axis the x-axis and tangent at the vertex the y-axis and blah blah blah. You don't have the choice. Suppose someone told you, well, I have a point S, which is say x1 comma y1, right? The focus. This is the axis, and they told you that this is the directrix. This is the directrix, which is say some Lx plus my plus n equal to 0 is the directrix. Right? This is the directrix, this is the focus. And then they said this is a point P and it traces a parabola whose focus is S and whose directrix is Lx plus my plus n equal to 0. Find the equation of the parabola. In this case, you would neither get y equal to a quadratic in x or x equal to a quadratic in y. You will get a more general form of the equation of a parabola. In fact, the most general form of the equation of a parabola would be obtained if this was the situation. Why? Because now the physicality will still be deployed. Distance of s from P will be equal to distance of P from the directrix. For any xy that lies on the parabola, we must have SP equal to PM. That's cardinal, that's fundamental. Right? SP squared therefore would be PM squared. SP squared would be PM squared. What is SP squared? For any xy on the parabola, x minus x1 whole squared plus y minus y1 whole squared. That's SP squared. Right? And PM squared is square of the distance of the point P from this line. How do you find the perpendicular distance of P from this line? Replace this x by this x, replace this y by this y, take the modulus divide by root L squared plus M squared, that will give you the perpendicular distance, right? So square of the perpendicular distance would be Lx plus My plus N whole squared divided by L squared plus M squared. Yes or no? Square of the perpendicular distance of P from this line. This is what you get, right? Now, the equation then will turn out to be of the following kind when you. So this would be the equation of the parabola whose focus is x1, y1, whose directrix is Lx plus My plus N equal to 0. Now, can you tell me what would be the latest rectum of this parabola? See, this length would be semi-latest rectum, isn't it? So double of this, double of SZ would be the latest rectum of the parabola. SZ would be the semi-latest rectum, right? Distance of focus from the directrix would be semi-latest rectum, right? So L, the semi-latest rectum, is distance of x1, y1 from this line. That is, let me call it semi-latest rectum, SLR. Semi-latest rectum, I am not using L because L has been consumed here. So semi-latest rectum would be mod of Lx1 plus My1 plus N divided by root L squared plus M squared. This length is semi-latest rectum. So twice of this would be latest rectum of the parabola, right? Yes or no? Notice that when I collect terms here, then the form of this equation of the parabola would be as follows. It will be like some ax squared plus some 2hxy, there will be xy terms, there would be y squared term, there would be 2gx plus 2fy plus c equal to 0 would be the form of the equation of this parabola, yes or no? Which is a generalized equation of second degree in x and y. This is a generalized equation of second degree in x and y. In x and y. Now, there is a property associated with this. For this, did I tell you the condition for which it's going to represent a pair of straight lines? Now, there is an inherent condition that would emerge for this to represent a parabola, right? Notice the following simple observation, but can I remove the clutter from here? Look. Do you all understand that when I consolidate terms, this would be the form of this equation, right? Now, notice what would be A here? L squared x squared, L squared x squared would get cancelled, so M squared would be, see, L squared plus M squared into x squared minus L squared x squared. So A would be M squared. Do you realize that? A would be M squared. No. See, x square would have L squared plus M squared coming from here, and would L squared would get subtracted. So A will turn out to be M squared, coefficient of x squared will turn out to be M squared, and coefficient of y squared B. See, y squared into L squared plus M squared minus M squared will give me L squared, coefficient of y squared would be M squared, L squared. Now, coefficient of xy, there will be only one term that will be coefficient of xy, which would be, realize that 2lm xy, isn't it? 2lm xy. So 2h is in this case, so minus 2lm is minus 2lm, yes or no? Transposed on this side, everything I have transposed on this side, right? Therefore, h is lm, right, or minus lm, or h squared is L squared M squared But that's AB, isn't it? L squared is B, M squared is A. So H squared is AB. Yes or no? Huh? What? Prince? No, didn't understand this. Semi-vertical, semi-horizontal nod is confusing. This is explicit. This is explicit. This is fuzzy logic. So, for this to represent a parabola, we must have H squared equal to AB. For this to represent a parabola, we must have H squared equal to AB. That's important. For a generalized second degree equation in x and y to represent a parabola, H squared must be equal to AB. Clear? Sounds all right? No, why should G and X F be 0? Of course not. There is a coefficient of X here. There is a coefficient of X here. Why should that be 0? No, not necessarily. Suppose, there's one more condition, that generalized discriminant should not be 0. That delta should not be 0. You know the delta that we obtained, remember this delta? AHG, right? That determinant should not be 0. Now, suppose someone gave you the axis. Someone gave you the axis of the parabola, say was Lx plus My plus n equal to 0. Someone gave you the axis of the parabola. Okay. And they gave you the vertex V. Vertex V was, say, x0, y0, which will always lie on the axis. Which will always lie on the axis, right? And then they said, find the equation of the parabola. Find the equation of the parabola. So, first of all, the tangent at the vertex would be perpendicular to the axis. Yes or no? Yes. This is the tangent at the vertex. This is the tangent at the vertex perpendicular to the axis, and a line perpendicular to this line would be given by mx minus ly plus lambda equal to 0. Any line perpendicular to this line must be of this form. Yes or no? Yes. And how do you find lambda? x0, y0 lies on the line, so you can find lambda. x0, y0 will, the vertex will lie on the tangent at the vertex. So x0, y0 satisfies this equation, and that will give you access to lambda. So lambda is known to us, right? So this is the tangent drawn at the vertex. Now the property that we learned was any point on the parabola would be such that square of its distance from the axis must be latest rectum into distance from the vertex. Now therefore tangent to the vertex. Therefore, another fact that you need about the parabola in order to actually determine the parabola is the latest rectum. So suppose they told you the latest rectum is say 2L0. 2L0 is the latest rectum of this parabola. L0 is the semi-latest rectum, 2L0 is the latest rectum, which is a property of the parabola. Right? Now, let me apply that condition. Square of the distance from the axis equals latest rectum into its distance from the tangent drawn at the vertex. So if Px comma y be any point on the parabola, right, then square of its distance from the axis right? That means distance of this xy from this line, how do you obtain that? Replace this x by this x, this y by this y, divide by root L squared plus m squared and square the whole thing. That will be square of the distance from the axis, right? This is the axis I've written. So Lx plus my plus n whole squared divided by L squared plus m squared is square of the distance of the point P from the axis, right? That must be equal to latest rectum LR into distance from the tangent drawn at the vertex, distance from the tangent drawn at the vertex. That means distance from this, that means mod of mx minus ly plus lambda, right? Distance of this xy from this line divided by root L squared plus m squared, yes or no? That's the equation of the parabola. Notice that we are not done. Not done. I would have to strip the modulus out. I would have to strip the modulus out. Right? You know what I'm saying? Realize that with this being the axis and this being the tangent at the vertex and latest rectum being this length, there are actually two positions of the parabola. See, if this is the axis and if this is the tangent drawn at the vertex, then the parabola, this will be the vertex. The parabola could either be like this or could be like this. There are two positions of the parabola, with this being the latest rectum or this being the latest rectum, right? That's a mere length, right? So which is what happens actually, you know, if I strip the modulus, then I get both the parabolas. Plus sign will give me one parabola, minus sign will give me the other parabola. If I use the plus sign, that will give me equation of one of the parabolas. If I use the minus sign, it will give me the equation of the other parabola, right? Both these parabolas are obtained here. Now, in order to uniquely determine the parabola, I would have to deploy another condition. Somebody would have to tell me whether the focus lies here or the focus lies there. For this parabola, the focus will lie here. For this parabola, the focus will lie here. Yes or no? Yes. Right now? Now, suppose, I hope I'm not confusing you. You are all in sync with me. Now, suppose they told you that the focus S is x1, y1. Suppose they told you the focus S is x1, y1. Then the parabola is unique. Now, if they told you the focus is x1, y1, then the parabola is indeed unique. Now, the choice of the plus or the minus sign would have to be made. Since the parabola is unique, I can't live with both the signs. I would have to reject one, accept the other one. Right? Yes. How do I do that? Whether I select the plus sign or the minus sign given the coordinates of the focus? The following then. What would have to be done is, realize that this is the tangent drawn at the vertex. The focus S and the focus P are on the same side of this line. Therefore, this point and this xy will produce the same sign on this? Yes. Yes or no? Right? Which means the sign produced by S in this expression is going to be mx1 minus ly plus ly1 plus lambda. Which could, right? The sign produced by S on this line is going to be the sign of this expression, right? Say if it is greater than 0, say if it is greater than 0, then this xy will also produce a positive sign. This xy will also produce a positive sign. Why? Because they lie on the same side. That means mx minus ly plus lambda must also be greater than 0 for any xy on the parabola, right? Now, this is non-negative, so this whole thing would have to be then non-negative, right? Mx minus ly plus lambda is positive, so I'll select a plus sign. That will be the required equation of the parabola, right? All that I'm saying is, see, these are two possible parabolas with the given set of conditions. Now, if I stipulated the focus for you S x1, y1, I would have to know which of the two. Then the parabola is unique. Then I know that the parabola is like this. if I give you the if I give you the focus, right, then I can't say the parabola would be plus minus this. The parabola would be one of the two, right? Now notice that x1 y1 and any point xy on the parabola satisfying this condition, they lie on the same side of the tangent at the vertex. Therefore, this s x1 y1 and this p x comma y will produce the same sign on this, right? Suppose this x1 y1 produces a positive sign on this expression, then this xy will also produce a positive sign on this expression, in which case mx minus ly plus lambda will be positive, right? So then if this is positive, then this whole thing is non-negative. So in order to make this non-negative, I will take a plus sign. If however this was negative, if the focus produced a negative sign, then the xy will produce a negative sign, then I will take a minus sign on this, so that this whole thing turns out to be non-negative, because then this is negative into negative, it will turn out to be a positive number. Do you then understand? So then what I have actually given to you is the most general form of the equation of a parabola. In this case, the axis is neither parallel to the x-axis nor parallel to the y-axis, but inclined to both in a very general sense, and it will be represented by the generalized equation of second degree in x and y. Clear? Now with some of these things in place, let's obtain some more results, taking the general equation y square equal to 4ax of a parabola into account. Some more relevant results, but each of these results would have a physicality associated with it, which could then be adapted towards the generalized equation of the parabola, right? So now we will look at this parabola y square equal to 4ax. 4a the lattice rectum, the axis of symmetry being the x-axis, y square equal to 0. This is this parabola y square equal to 4ax, right? This is a point P x1 comma y1 on the parabola, right? I want to be able to find the equation of the tangent at x1 y1. I want to be able to find the equation of the tangent at x1 y1. Right? Now I know a point on the tangent, I therefore need the slope of the tangent to be able to find the equation of the tangent. Now if this is theta, the slope of the tangent tan theta, slope of any curve at a given xy, is given by dy dx at that xy. That means in order to find the tangent at x1 y1, I need to find dy dx at x equal to x1 and y equal to y1. That will give me the slope of the tangent at any x1 y1 of a curve, right? Now in this case, y squared equal to 4ax, if I differentiate with respect to x, I get 2y dy dx equal to 4a, right? Or dy dx equal to 2a by y at any xy. So if I have to say dy dx at x1 y1, then that's going to be 2a by y1. That's going to be 2a by y1, replace x by x1 and y by y1. So I get 2a by y1 is the slope of the tangent at x1 y1, right? Now the equation of the tangent, therefore, so that's the slope of the tangent. The equation of tangent at x1 y1 is going to be given by y minus y1 is slope 2a by y1 into x minus x1. Y minus y1 by x minus x1 is slope at x1 y1, which is 2a by y1. Yes or no? Right? Which then reduces to y1 minus y1 squared is 2a into x minus x1. Yes or no? Hey, but x1 y1 is a point on the parabola, so y1 squared must be 4a x1. Y1 squared must be 4a x1 because x1 y1 is a point on the parabola also, so it satisfies the equation of the parabola. Now replace this y1 squared by 4a x1. So equation of the tangent y1 minus 4a x1 equals 2a into x minus x1. That's the equation of the tangent at x1 y1, right? If I transpose this on this side 4a x1, then I end up getting y1 equals 2a into x plus x1. y1 is 2a into x plus x1 is the equation of the tangent at x1 y1, yes or no? Yes, right? Which is to say that y1 for any x1 y1, the equation of the tangent is going to be minus 2a into x plus x1 equal to 0 is the equation of the tangent at any x1 y1. Equation of the tangent at any x1 y1 is this, right? What? This you didn't understand. Equation of a line passing through x1 y1 and having slope m. क्या होता है भाई? Y minus y1 by x minus x1 is the slope of the line. So y minus y1 is slope m into x minus x1. नहीं? Y minus y1 by x minus x1 is the slope of the tangent 2a by y1. Multiply. So y1 minus y1 squared, etc. Right? But x1 y1 is a point on the parabola, so y1 squared is 4a x1. Plug into that, you get this equation of the tangent at x1 y1. Confusing? No? Now, henceforth, like we've done in circles, we'll call this expression as t. This expression would be referred to as t. y1 minus 2a into x plus x1 is an expression called t.
So what if I didn't know calculus?
Then you can't find the slope. I am so sorry. If you didn't know calculus, you can't find the slope here. Freeze. That's why you know that basics were covered earlier. Slope of the tangent. In case of a circle, it was not required because we knew a property of the tangent, that the tangent is perpendicular to the radius. In a parabola and henceforth for all other sections, you have to know this bit of calculus. Right? Got me? The entire notion of tangent is actually calculus. You know, calculus started with the business of finding tangents. You know, that is where they started with calculus. So, don't have an option, sorry. Huh? So, call this expression t, y1 minus 2 into x plus x1 as t. And this is just an expression. If x1 y1 is a point, on the parabola, then t equal to 0 represents the equation of the tangent at x1 y1. But otherwise, the expression t would be defined for any x1 y1 on, inside or outside the parabola. The expression t is defined like this. But if x1 y1 is a point on the parabola, then t equal to 0 will represent the equation of the tangent at x1 y1. Be very clear about it. The expression t is not limited to where the point x1 y1 lies. It could lie on the parabola, inside or outside the parabola, right? That's needlessly restrictive. The expression t is defined for all x1 y1 in the plane. But t equal to 0 if x1 y1 lies on the parabola represents the equation of the tangent at x1 y1. Clear? Now, if this point if this point x1 y1 is parametrically represented by t, right, then x1 would be at squared, y1 would be 2at, right. Then the equation of the tangent at x1 y1 would be y1 is 2a into x plus x1 is the equation of the tangent. I could have written this as y into 2at, y1 is 2at is 2a x plus at squared. That's the equation of the tangent at any t of the parabola, standard parabola y squared equal to 4ax, right. So this gives me like a yt equal to x plus at squared at any given t, where t represents the point at squared comma 2at, right. The equation of the tangent at any given t therefore is 1 by t into x plus at. Right, where the slope of the tangent at any given t then will be 1 by t. Do you see that? 1 by t would be the slope of this line. So if a tangent is drawn at any given t, the slope of the tangent could also be written as 1 by t for a standard parabola. The slope of the tangent is written as 1 by t for a point t on the parabola y squared equal to 4ax. Have I confused you? No? T is a parameter. T can have any value. Different t's will give me different points on the parabola. For any given t, the corresponding point on the parabola would be at squared comma 2at, right. T can have any value from minus infinity to plus infinity, and for every such real t there is going to be a point at squared comma 2at on the parabola, right. So for any given t, the slope of the point would be at squared comma 2at, and the slope of the tangent would be 1 by t, as you can see. Yt is x plus at squared, yes or no, right. Now can I wipe this off? Say this is a parabola y squared equal to 4ax, and there is a line y equal to mx plus c. There is a line y equal to mx plus c, right, is a line. Now that line could have three possible orientations. One, imaginary points of intersection with the parabola. Imaginary intersection points with the parabola, that's one possibility, right, right. Distinct real points a b, a and b of intersection with the parabola. Distinct real points a and b of intersection with the parabola, right, or coincident real points with the parabola. In this case a and b coincide, right, a b coincide, coincident real points, and when this happens the line is rendered a tangent. That's when the line becomes a tangent. When a and b are real and distinct, it becomes a chord or the secant, chord or a secant, right. Now how do I find a and b real or imaginary? A and b are actually intersection points of this parabola with this line. A and b are actually intersection points of the parabola with this line, yes or no, right. So if I solve these two equations, then I am talking of an xy that satisfies this equation as well as this equation. What are those xy's? Those xy's are xy's of a and b. On solving these two equations, I get the xy that lies on the parabola as well as on the line. That means those would be points of intersection of the parabola with the line, yes or no?
Yes, sir.
Right. So, let me solve these two equations to get access to A and B. What we do here is y squared equal to 4a x. X I can write as y minus c by m. This will give me two values of y. One would be y of a, one would be y of b. Yes or no? Gives me two roots of this quadratic would be y of a and y of b. Isn't it? The roots of this quadratic would be y of a and y of b. Now, this I can write as a customary traditional y squared minus 4a by m into y plus 4ac by m equal to 0. That's a conventional quadratic in y squared minus 4a into y by m plus 4ac by m equal to 0, right? Now, if you want this to happen, right, let me call this 1 where it becomes a chord, let me call this 2 where it becomes a tangent, let me call this 3 where there are no real points of intersection with the parabola, right? Now, for this, ya and yb must be real and distinct. For the roots of this to be real and distinct, discriminant must be greater than 0, right? So, for config 1, ya and yb must be real and distinct, right? Discriminant must be strictly greater than 0 for the parabola, right? For this quadratic, sorry. So, that means 4a by m whole square minus 4a by m into 4ac by m. See, b squared minus 4ac must be greater than 0. Yes or no? Right? Or this gives me c less than 4a by m, c less than a by m, c less than a by m is what I get, right? If I put discriminant greater than 0, so this would be a chord if c is less than a by m, then this y equal to mx plus c will become a chord of the parabola if c is less than a by m. See, this gives me c less than a by m, isn't it? Now, for config 2, can I wipe this off? A and B must be coincident, A, B coincide, y of A equals y of B. This quadratic must have equal roots, so discriminant must be equal to 0, and that will give you c equal to a by m, right? Instead of greater than, less than inequality, you will have the equal sign, that will the same expression, but c will be a by m. That means if this line has to be a tangent to the parabola y squared equal to 4ax, c must be a by m, c must be a by m, right? Yes or no? And so that's for config 2. That means for y equal to mx plus c to become a tangent to the parabola, c must be a by m. Now, for this to happen, for this, discriminant must be less than 0, discriminant of this quadratic must be less than 0, and that will give you c greater than a by m, that will give you c greater than a by m, right? No real points of intersection with the parabola. So, when c is a by m, it becomes a tangent. When c is less than a by m, it's a secant or a chord. When c is greater than a by m, it has no real points of intersection with the parabola. Yes or no?
Yes.
Right? Can I wipe this portion off?
Yes.
Which means y equal to mx plus c, where c is a by m, will always be a tangent, to the parabola y squared equal to 4ax. Tangent to the parabola y squared equal to 4ax. Y equal to mx plus c, where c is a by m, will always be a tangent to the parabola y squared equal to 4ax. That means y equal to mx plus c, where c is a by m, will always represent a tangent to the parabola. Yes or no? m is a fixed number, it's going to be a certain fixed tangent. If m is a parameter, it will represent a family of tangents. If you vary m, you get different tangents to the parabola. Then it can be looked upon as family of tangents to the parabola. Yes or no? Hmm? You know what I'm saying? Now, the question then is, given a point, how many tangents could I draw to the parabola? Given a point, I'm so sorry. Given a point, how many tangents could I draw to a parabola? That's the question that I also want to address, right? Let's figure out. Okay. Say, this is a parabola, y squared equal to 4ax, right? And say this is a tangent. This is a tangent, y equal to mx plus a by m. A tangent y equal to mx plus a by m is a tangent, right? And say this tangent passes through a point P x1 comma y1. Let's say this tangent passes through a point P x1 comma y1. And what's the slope of the tangent? M. Slope of the tangent is m, right? So since this tangent passes through x1 comma y1, x1 y1 will satisfy this equation. So we end up getting y1 equal to mx1 plus a by m. Since x1 y1 lies on the tangent of slope m, right? Now this could be rewritten as, multiplying throughout by m, I could have rewritten this as x1 into m squared minus y1 into m plus a equal to 0. Yes or no? Now what does it mean? It means that for a given x1 y1, if you solve for m, you would get the slope of the tangent drawn from x1 y1 to the curve, right? For a given x1 y1, if one solves for m, one gets the slope of the tangent from x1 y1 to the curve. Yes or no? If you solve this quadratic in m, you get the slope of the tangent drawn from x1 y1 to the curve. Yes or no?
Yes.
What? Are you messed up? No? But you're getting two values of m. That means in general two tangents could be drawn from x1 y1 to the curve. See, you are getting a quadratic in m, two values of m would emerge, meaning two tangents could be drawn from x1 y1 to the curve, right? x1 into m squared minus y1 into m plus a equal to 0. x1 y1 is a certain point. M is the slope of the tangent drawn from x1 y1 to the curve. From x1 y1, m is the slope of the tangent drawn to the curve. Yes or no? Huh? And since two values of m appear, m1 and m2 are the roots of this quadratic, which means in general two tangents could be drawn from x1 y1 to the curve, right? Which means if there is a point P x1 y1, then two tangents could be drawn to the curve. One would be of slope m equal to m1, the other one would be of slope m equal to m2. Yes or no? Where m1 and m2 are the roots of this quadratic in m. m1 and m2 are the roots of this quadratic in m, right? Which means m1 plus m2 slopes of the two tangents that could be drawn from x1 y1 to the curve would be such that m1 plus m2 would be y1 by x1 minus b by a, sum of the roots of this quadratic. And m1 m2, the product of the roots, is going to be a by x1. Yes or no? Yeah, you have a question? Now. अरे बाबा थोड़ा सा पढ़ाने देना यार. Now the question is, what's the guarantee that m1 and m2 are real numbers? Only if m1 and m2 are real numbers do you have real tangents from x1, y1, isn't it? Yes. Right? In order that you could have distinct tangents, two distinct real tangents from x1, y1 to the curve, m1 and m2 should be real and distinct, right? So, for tangents to be real and distinct, tangents drawn from x1, y1 to be real and distinct, m1, m2 should be real and distinct. Right? Now, for m1 and m2 to be real and distinct, discriminant must be greater than 0. Discriminant greater than 0 means y1 squared minus 4a x1 must be greater than 0. Hey, what is this? S1. This is S1. S1 greater than 0 means x1, y1 must be outside the curve. X1, y1 must be outside the curve. So, for all points outside the curve, two real and distinct tangents could be drawn to the curve. Right? For tangents to be coincident, discriminant must be equal to 0. That means y1 squared must be 4a x1, or P lies on the parabola. See, this case d greater than 0 is this case, isn't it? D greater than 0. Tangents from x1, y1 to be real and distinct, P must be outside the parabola, as you can see here, right? If you have a point P on the parabola, then the tangents drawn would be coincident and real, right? For tangents to be imaginary, that means non-real. For imaginary tangents, m1 and m2 must be imaginary, must be complex. The roots of this must be non-real. That means discriminant must be less than 0, right? And discriminant of that quadratic less than 0 really means y1 squared minus 4a x1 less than 0. That means s1 less than 0. That means x1, y1 must be inside the parabola. Therefore, from points inside the parabola, you can't draw real tangents. From points outside the parabola, you can draw distinct and real tangents. From points on the parabola, you can draw real and coincident tangents. For m1, m2 to be complex, that means non-real tangents, discriminant less than 0, that will give you what discriminant of this quadratic y1 squared minus 4a x1 less than 0. Yes or no? Right? Huh? Now, for tangents to be perpendicular, m1, m2 must be minus 1, right? m1, m2 equal to minus 1 means a by x1 must be minus 1. That means x1 plus a must be 0. That means x1, y1 must lie on the directrix. If for the point P x1, y1, x1 is minus a, then P must lie on the directrix, yes or no? P must lie on the directrix of the parabola. Does it not mean this? That means if you took any point on the directrix and drew two tangents to the parabola, then the two tangents ought to be orthogonal or perpendicular to each other. Am I going too fast or is it okay? So, if this was the parabola, see, x1 equal to minus a means x1 y1 must be on the directrix x equal to minus a. So, if you took any point on the directrix and then the two tangents drawn to the parabola would have to be necessarily perpendicular. From any point P on the directrix, the two tangents PT1, PT2 must be perpendicular to each other. From any point on the directrix, the two tangents drawn to the parabola have to be perpendicular. Is it confusing? No? You are all registering everything that I am communicating, right? Now, this is a very important property of the parabola. If you draw tangents from any point on the directrix, the two tangents have to be perpendicular to each other or orthogonal, right? And therefore, the directrix is the director circle of the parabola. What is the director circle? The director circle is the locus of points such that tangents drawn from those points to the parabola are perpendicular to each other. Tangents from the directrix are perpendicular to each other. Tangents from the directrix are perpendicular to each other. Therefore, the directrix must be the director circle of the parabola. It's a circle of infinite radius. It's a circle of infinite radius, isn't it? That's what it is. So, the directrix is really the director circle of the parabola. From any point on the directrix, if you choose to draw a pair of tangents, they would always be orthogonal or perpendicular. Right now? Now, look, tangent drawn at any point of t of the parabola, say standard parabola y squared equal to 4ax, tangent at any t, t means a point at squared comma 2at, tangent at any t means at squared comma 2at is going to be yt is x plus at squared. I told you this, right? y1 is 2a into x plus x1, replace y1 by 2at, x1 by at squared, you get the equation of the tangent at any t of the parabola. Now, if this tangent passes through x1 y1, if it passes through x1 y1, then x1 y1 will satisfy this equation. x1 y1 is a point on the tangent drawn at t. x1 y1 is a point on the tangent drawn at t. Then y1t is x1 plus at squared. Where t represents a point. T represents a point on which a tangent is drawn from x1 y1 to the parabola, yes or no? See what it gives me. There is a point P, and from this point P I can draw a tangent at a point which is t. That means at a point at squared comma 2at. Where, how do you obtain this t? When you solve this quadratic, you get the t at which tangents could be drawn from a point x1 y1 to the parabola. Yes or no? This is a fixed point x1 y1, right? When you solve for t, you would get the tangents drawn from x1 y1 to a point t of the parabola. But do you realize you are getting two values of t? That means from a point P x1 y1, tangents could be drawn to t equal to t1 and t equal to t2. From a point P x1 y1, tangents could be drawn to t equal to t1 and t equal to t2. Why? Because it's a quadratic in t. You will get two values of t. Yes or no? t1 and t2 are the roots of this quadratic in t. That means at squared minus y1t plus x1 equal to 0 has roots t1 and t2, where t1 and t2 are points where the tangents are drawn from x1 y1 to the parabola. Yes or no? Right now? So if you solve for t1 and t2, you would know these points of tangency from x1 y1, right? Say t2 means this point is a t2 squared comma 2a t2. t1 means this point is a t1 squared comma 2a t1. Now rephrasing the whole thing. If a tangent is drawn at t2, it will be this tangent. If a tangent is drawn at t1, it will be this tangent. x1 y1 is what? The intersection of tangents drawn at t1 and t2. Yes or no? x1 y1 is what? The intersection of tangents drawn at t1 and t2, where what are t1 t2? t1 t2 are the roots of this quadratic in t. t1 t2 are the roots of this quadratic in t. Yes or no? Yes, sir. Right. So suppose someone gave you t1 t2 and said find x1 y1. Suppose someone told you there is a point t1 on the parabola, there is a point t2 on the parabola. Tangents are drawn at t1 and t2. At what point do these tangents intersect? They intersect at x1 y1. So given t1 t2, I want to find x1 y1 now. Given t1 t2, the points of tangency, I want to find the point where the tangents intersect. That means x1 y1. Simple. Sum of the roots t1 and t2 are known, right? Sum of the roots t1 plus t2 is what? Minus b by a. That means y1 by a. And t1 t2 is x1 by a. Hey, this gives me x1 equal to a t1 t2 and y1 equal to a into t1 plus t2. Yes or no? That means if I draw a tangent at t1, I draw a tangent at t2, then the tangents intersect at a t1 t2 comma a t1 plus t2. Very useful result. Very useful result. For a parabola, if a tangent is drawn at t1 and t2, then the tangents intersect at a point P, which is x coordinate a t1 t2, y coordinate a t1 plus t2. Yes or no?
So for this type of question, A will be always given.
Yeah, of course. The parabola is given y squared equal to 4ax, so a is obviously known. So if you draw a tangent at t1 and t2, then the tangents intersect at a t1 t2 comma a t1 plus t2. Right? Hey, now again, just to check one of the propositions that I derived earlier from these considerations. See, I told you if a tangent is drawn at t, then the slope of the tangent would be 1 by t. Right? Yes or no? Yes. So what's the slope of this tangent drawn at t1? 1 by t1. What's the slope of this tangent drawn at t2? Right? Now if, say, let me call it AB. If PA, tangent PA perpendicular to tangent PB, then M1 M2 would be minus 1. Then M1 M2 would be minus 1. Yes or no? If M1 M2 is minus 1, means 1 by T1 T2 is minus 1. Yes or no? That means x coordinate of the point P, which is a T1 T2, would be minus a, which then is a point on the directrix. So if tangents are perpendicular to each other, then they must intersect at x equal to minus a, which is a point on the directrix of the parabola. Got me? Sounds fair? Now, some results which I derived in circles, the form of the results get replicated in parabola, ellipse, hyperbola, etc. One of them is the following. See, I have defined S and I have defined T for you, right? Now, if there is a point P, x1, y1, then like we've obtained, from this point P you could draw two distinct real tangents if P is outside the parabola, right? The two distinct real tangents to the parabola would be these, right? A and B would be points of tangency. A and B would be points of tangency. So from P, two distinct real tangents are drawn. A and B are points of tangency. Right? Then this AB is called the chord of contact with respect to P. Chord of contact with respect to P, x1, y1. And do you remember how we obtained the chord of contact? Chord of contact was T equal to 0 in a circle. Same thing. The equation of the chord of contact would be T equal to 0. Same thing we had in circles. Remember? So equation of the chord of contact would be y1 minus T is, the expression T is defined as this. x1, y1, if x1, y1 is a point outside the parabola, if x1, y1 is a point outside the parabola, then T equal to 0 gives me the equation of the chord of contact with respect to x1, y1. Right? We had an identical thing going on in circles. Right? So T equal to 0 represents the chord of contact with respect to an external point x1, y1. And a similar result, if this is a parabola, y squared equal to 4ax, all of it is y squared equal to 4ax. And if M is the midpoint of AB, having coordinates x1, y1, then the equation of the chord in terms of its midpoint was T equal to S1, was T equal to S1. So equation of the chord in terms of its midpoint x1, y1 is going to be T equal to S1, right? Where T would be, as far as this point is concerned, y1 minus 2a into x plus x1 equals S1. S1 is y1 squared minus 4a x1, that's S1. T equal to S1 gives me the equation of a chord of y squared equal to 4ax in terms of its midpoint x1, y1, right? T equal to S1 is the equation of the chord in terms of its midpoint x1, y1. Yes or no? Same result really. Now, so I'm not going to redo these results for you. They have exactly the same proof as they had in circles, but I want you to take notice of these results. Now, look, say this is a parabola y squared equal to 4ax, parabola y square equal to 4ax. Okay. And this is a certain chord of the parabola. This is a certain chord of the parabola AB. Let's say the equation of this chord is y equal to mx plus c is the equation of this chord. Now when I solve this equation with this, I would get the intersection points between the parabola and the chord, right? Yes or no? Now what I do is y equal to m, this x I replace by y squared by 4a plus c, which will give me what? The y of the intersection between the parabola and the chord, quadratic and y. So two values of y, one will be y of a, the other one would be y of b, right? So m by 4a into y squared minus y plus c is 0. It will give me the y of the intersection between the parabola and the chord, right? We'll have roots ya and yb, we'll have roots ya and yb, y of that end and y of this end, right? Right, where ya plus yb is what? 4a by m, 2a by m minus b by, oh sorry, 4a by m. 4a by m, y plus yb would be 4a by m. Yes or no?
Yes, sir. Yes, sir.
Very useful result. Which means, see, this is a chord of slope m, right? And y of a plus y of b turns out to be 4a divided by the slope of this chord. 4a divided by the slope of this chord, right? Now, if I take another chord of same slope parallel to this line, then c and d, what would be y of c plus y of d? 4a by m, right? If I take any chord parallel to this chord, then y of this plus y of this will always be 4a by m. Yes or no?
Yes, sir.
That means if I took a system of parallel chords, then some of the extremities of the y will be the same for all the chords. Some of the extremities of the y's would be the same for all the chords and will be equal to 4a by m. Yes or no?
Yes, sir.
Right? Which means, no confusion, right? Which means, say if this was a parabola and I had a system of parallel chords, each of slope m, system of parallel chords, each of slope m, system of parallel chords, each of slope m, right? And I took y of this end plus y of this end. For any chord, it's going to be the same for all the chords, 4a by m, right? Now, if I took the midpoint of any of these chords, if m is the midpoint of AB, for any of these parallel chords, then what would be y of m? Ya plus yb divided by 2, which is 2a by m, which is again the same for all the chords. That means whether I took the midpoint of this, or 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 I took the midpoint of this, the y's of all the midpoints will be the same and will be 2a by m. Yes or no?
Yes, sir.
Right? Which means say this was the axis of the parabola. This was the axis of the parabola. In this case, it turns out to be the x-axis for the parabola y square equal to 4ax is also the x-axis. And I had a system of parallel chords. And I had a system of parallel chords, each of slope m, each of slope m, and I took the midpoint of this chord, M1. I took the midpoint of this chord, M2. I took the midpoint of this chord, M3, and so on and so forth, the midpoint of these chords. Then y of the midpoint of all these chords would be 2a by m. Y of the midpoint of all these chords would be 2a by m, yes or no? Yes, which means if I join these midpoints, M1, M2, M3, Mn, this will be the diameter of the parabola. This will be a diameter of a parabola referred to a system of chords of slope m, This will be a diameter of the parabola if I joined all the midpoints. Right? Yes or no? And the y, all the midpoints will lie on y equal to 2a by m. All the midpoints will lie on y equal to 2a by m. Right? That means the equation of the line joining the midpoints of all these chords would be y equal to 2a by m. Equation of the line joining the midpoints of all these parallel chords would be y equal to 2a by m, which is parallel to the axis of the parabola. The equation of the diameter for the system of chords is y equal to 2a by m, which is a line parallel to the axis of the parabola, which is in some cases the x-axis need not be the axis, some other line would be the x-axis, then the diameter will be parallel to that axis. Right? That's a physicality you must bear in mind. Right? So which is a line parallel to the axis of the parabola. And the axis need not always be the x-axis. The physicality is that the diameter of a system of parallel chords will always be parallel to the axis of the parabola. It so happens that in this case the axis and the x-axis are synonymous. Right? So this is the diameter, right? And not only that, look, there was this system of parallel chords, each of slope m, system of parallel chords each of slope m. I joined their midpoints M1, M2, M3, M, and I got the diameter. Whose equation was y equal to 2a by m. Right? Now the diameter would intersect the parabola only at one point. What point is that? This point, P. Right? What are the coordinates of this point? Some x would be some x1 and y1 would be 2a by m for this. Right? This diameter intersects the parabola at x1 comma y1, where y1 is 2a by m. Yes or no? Yes. Now, in a parabola y squared equal to 4ax, realize that the slope of the tangent at x1 y1 is 2a by y1. Right, at the very onset I derived this. See, if you differentiate this, 2y dy dx is 4a. So dy dx would be 2a by y. So at y equal to y1, dy dx would be 2a by y1. That's the slope of the tangent. So if I draw a tangent at P, then the slope of that tangent, see, each of these lines is of slope m. Right? Each of these lines is of slope m. The slope of the tangent would be 2a by y1. 2a by y1, but that's the same as m. That's m. That means what? That means the tangent at the extremity of a diameter will be parallel to the system of parallel chords. You know what I'm saying? If this is a diameter and this is a system of parallel chords, then the tangent drawn at this point, where the diameter intersects the parabola, will be parallel to the system of parallel chords. Yes or no? Got me? Useful result. Keep tab on this. Let me know if you're done so that I could wipe this off. Now, a very pertinent chord of the parabola is a focal chord. There could be many chords, but of these many chords, those that pass through the focus will be focal chords, would be focal chords, right? Say in a parabola, y squared equal to 4ax. This is S, the focus, which would be A0. AB is a focal chord. AB is a focal chord of the parabola, right? AB is a focal chord of the parabola. Different focal chords will all pass through S, but will differ in slopes. Right? So if this is the slope M, right? Then the equation of the focal chord would be is going to be y minus c. It passes through A0 and has slope M, right? Different focal chords will subscribe to different values of M, right? So y minus 0 is M into x minus a. Y minus 0 is M into x minus a, right? Now, to find the intersection of the focal chord with the parabola, right? To find the intersection of the focal chord with the parabola, I'll solve this equation with this equation, then I'll get the extremities of the focal chord. This is what transpires, right? If I solve this equation with the equation of the parabola, then I'll get the two points A and B. The coordinates of the 2 points A and B is what we end up getting, right? Now, instead of solving this equation with this equation could be replaced by a parametric equation. That means any point on the parabola could have been written as x equal to 80 squared, y equal to 280. That's how you could write any point on the parabola, x equal to 80 squared comma y equal to 280. Now, the moment x and y are chosen in this form, then that point is always on the parabola. If a point is chosen as x equal to 80 squared, y equal to 280, perforce it has to be on the parabola. But now, if this xy also satisfies this equation, not only will it lie on the parabola, it will also lie on the straight line. Yes or no? If this xy is of this form, it has to be on the parabola. But now if this xy satisfies this equation as well, it has to also be on the focal chord, right? Yes or no? So now if I solve this with this, then I will get the t of the intersection between the parabola and the focal chord. Yes or no? If I plug in x equal to 80 squared here and y equal to 280 here, what would I get? I would get the t of the intersection between the parabola and the focal chord. Sounds good, right? Are you all convinced? Huh? So now plug in y equal to 280, y equal to 280, x equal to 80 squared. I get two values of t. These are the t's of the intersection between the parabola and the focal chord. Are you convinced completely about this? So the two values of t that I get from this would be t1 and t2. Would be t1 and t2, which would be roots of this. T would be t1 for this and t would be t2 for this, right? T1, T2 would be the roots of this quadratic in t, right? Which means, see, a gets cancelled. I end up getting t squared minus 2 by m into t plus a equal to 0. Right? Isn't it? T squared minus 2t by m minus a equal to 0. Oh, a gets cancelled, so 1. A gets cancelled, 1. Right? Which means the roots of this quadratic in t, the roots of this quadratic in t would be t1 and t2, which are extremities of the focal chord, right? And do you realize that although t1 plus t2 will depend on the slope of the focal chord, but t1 into t2 will not depend on m. Do you realize that? For a focal chord, then t1 into t2 is minus 1, which does not depend on m. That means will be true for all focal chords? Yes or no? That means if this was one focal chord with this extremity being t1, this extremity being t2, then t1 into t2 would always be minus 1. Yes or no? Right? So the t's at the extremities of a focal chord, any focal chord, the product of these t's for a standard parabola will always be minus 1. t1, t2 would be minus 1. That means if the t for this is 3, then the t for this would be minus 1 by 3. Right? Yes or no? Very useful result. Right? Now, an important corollary of this result. No confusion, right? Yes. Hey, so for this focal chord, say I draw a tangent at this extremity, I draw a tangent at this extremity. I draw tangents at A and B, right? Then the tangents intersect at P, where P would have coordinates A T1 T2, comma A T1 plus T2, a result that we obtained a little while ago. But if it's a focal chord, T1 T2 would be minus 1, right? For a focal chord, T1 T2 is minus 1. That means x of P is minus A. That means P lies on the directrix. Very good. And then the two tangents have to be perpendicular to each other. P lies on the directrix, because x of P turns out to be minus A, right? T1, T2 is minus 1, so x of P is minus A. P lies on the directrix. So which means leads us to a very important result. Two results. One, if this is a focal chord for a standard parabola, then the product of the two t's will always be minus 1 for all focal chords. Right? Two, tangents drawn at the extremity of the focal chord must intersect on the directrix and therefore must also be perpendicular to each other. Right? And again you can check the slope of the tangent drawn at T2 would be what? 1 by T2. Slope of the tangent drawn at T1 would be what? 1 by T1. Hey, now product of the slopes M1, M2 would be 1 by T1, T2, which is going to be minus 1 because T1, T2 is minus 1. That means the two tangents are perpendicular to each other. And that they intersect on the directrix. Right? And the converse of this result, which means So one thing, I repeat, if there is a focal chord, tangents drawn at the extremities will be perpendicular and would intersect on the directrix. 2, the converse of this result, that means if this is the directrix and if this is a parabola, and then if I draw the tangents, then the two tangents will be perpendicular to each other, and then the chord of contact will be a focal chord. The chord of contact will be a focal chord. If this is a point on the directrix, then AB, which is the chord of contact with respect to P, contact must be a focal chord, of the parabola, must pass through the focus. If you draw a pair of tangents from any point on the directrix, then the chord of contact will always pass through the focus, right? And they will always, and the tangents would be mutually perpendicular. This is by far the most commonly used results in parabola. See, there is a prerequisite for doing certain things. So I'll take a little detour and then come back to parabola. But then this one I need in order that you could understand the rest of the digression on parabola. So first of all, a little bit on polynomials. A polynomial of degree n in x is like a0 x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus an. That's a polynomial of degree n in x. Right? Now the important thing about this is that a0 should not be 0, because other coefficients could be 0, but a0 should be non-zero, because if a0 turns out to be 0, it will become a polynomial of degree n minus 1 in x. So for this to be a polynomial of degree n in x, a0 should not be 0. Other coefficients may or may not be 0, that's all right. Now a polynomial of degree n in x has exactly n roots. Real or complex, distinct or coincident. Has exactly n roots, real or complex, distinct or coincident. Say the roots are alpha 1, alpha 2, alpha 3, alpha n. Now that means this polynomial will vanish for x equal to alpha 1, will vanish for x equal to alpha 2, will vanish for x equal to alpha 3, and so on and so forth, right? Now if this polynomial a0 x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus an, right? If it vanishes for x equal to alpha 1, that means x minus alpha 1 must be a factor of this polynomial. X minus alpha 1 must be a factor of this polynomial. See, when you factorize a polynomial, are you creating an equation or an identity? Identity. Factorizing will always create an identity. Similarly, x minus alpha 2 will be a factor of this polynomial. X minus alpha n will be a factor of this polynomial, right? So these are all the factors of this polynomial, right? So this polynomial is identical to a0 into this. Why did I multiply with a0? Because the coefficient of x power n here is a0, coefficient of x power n here must also be a0. If two polynomials are identical, then coefficients of equal powers of x is the same in both polynomials, right? Now a0 is not 0, so I can divide by a0 both sides. If a0 is not 0, I could divide by a0 both sides. So if I divide by a0 both sides, this right hand side would be x minus alpha 1 into x minus alpha 2 into x minus alpha 3 into x minus alpha n equal to x power n plus a1 by a0 x power n minus 1 plus a2 by a0 x power n minus 2 plus an by a0. And this division was legal because A naught was non-zero, right? And what is it? Is it an equation or an identity? It's an identity. It's an identity, right? That means coefficient of x bar London here would be coefficient of x bar London there. Coefficient of x bar Patna here would be equal to coefficient of x bar Patna there, and so on and so forth, right? Now, let me expand the left hand side, okay? In descending powers of x, x into x into x into x, that makes it x bar n, right? The first term, yes or no?
Yes, sir.
Now, the next term, which is coefficient of x bar n minus 1, this is x bar n, the next term would be x bar n minus 1 into something, right? Now, x bar n minus 1, how do I obtain x bar n minus 1? How many factors are these? N factors, right? So what I do is, let me hide the first factor. Let me hide the first factor for a moment. Then x into x into x into x, that will make it x bar n minus 1 into minus alpha 1. That is minus alpha 1 into x bar n minus 1, right? So then one term would be minus alpha 1 into x bar n minus 1, yes or no? The other term. Hide the second term. Hide the second term. Are you confused? No? Hide the second term and multiply the x's of the remaining, x into x into x, x bar n minus 1 into minus alpha 2. So minus alpha 2 x bar n minus 1, that's going to be the second term. Right? Hide the third term, x into x into x into x, that's x bar n minus 1 into minus alpha 3. So plus alpha 3 and going this way up to plus alpha n. Yes or no? That will be the coefficient of x bar n minus 1. Clear? Now, coefficient of x bar n minus 2. Now, how many terms are these? NC1. NC1 terms, right? There are n of these numbers, taking them one at a time. That will give me NC1 terms here. Now, x bar n minus 2. Now, how do I obtain x bar n minus 2? I hide two factors. Then x into x into x, x bar n minus 2 into minus alpha 1 into minus alpha 2. That means plus alpha 1 alpha 2, right? So plus alpha 1 alpha 2. Then let's say I hide the second and the third factors, right? And then x into x into x, x bar n minus 2 into minus alpha 2 minus alpha 3, that makes it alpha 2 alpha 3. So plus alpha 2 alpha 3. And hiding two at a time and carrying this operation, I get all the coefficients of x bar n minus 2, alpha 2 alpha 3 plus alpha 1 alpha 3 and so on and so forth. All two pair products would be obtained. This would be sum of the product of these numbers taking two at a time. This is sum of the product taking one at a time. This is, and how many terms would be there in this? NC2 terms. Sum of the product taken two at a time. S2 would be, let's say, sum of the product taken two at a time, alpha 1 alpha 2 plus alpha 2 alpha 3, etc., which is sum of the product taken two at a time. Taking two at a time. NC2 terms in this S2, right? Then the next one, similarly, please check for yourself, would be like sum of the product taking three at a time, alpha 1 alpha 2 alpha 3 plus alpha 2 alpha 3 alpha 4, x bar n minus 3, which would be sum of the product taking three at a time, S3. How many terms would be there in this? NC3 terms would be there in this S3. And going this way, eventually, if I have a term like a x bar n minus r, then this will be accompanied with minus 1 to power r. See, taking 2 at a time would be minus 1 to power 2. Taking 1 at a time would be minus 1 to power 1. Taking 3 at a time is minus 1 to power 3. So taking r at a time, SR, sum of the product taking r at a time, NCR terms in this, minus 1 to power r. Yes or no? and then going this way up to minus alpha 1 into minus alpha 2 into minus alpha 3 into minus alpha n. That makes it minus 1 to power n alpha 1, alpha 2, alpha 3, alpha n, which is the product of the roots. Minus 1 to power n into alpha 1, alpha 2, alpha 3, alpha n, which is sum of the product taking all at a time. Because then there will be only one term. If you take all at a time in the product, there would be just one term, which also gives you the product. Sum of the product taking all at a time would be also the product of the roots. Yes or no? Right? So that's the left hand side, which is identical to the right hand side. So I can equate coefficients of equal powers of x on both sides. This is S1, sum of the roots, which is sum of the product taking 1 at a time. This is S2, sum of the product taking 2 at a time. This is S3, sum of the products taking 3 at a time. Now if I equate coefficients of equal powers of x on both sides, then S1, which is sum of the roots, which is alpha 1 plus alpha 2 plus alpha n, that will be minus a1 by a0. Tell me, minus the coefficient of the second highest power divided by coefficient of the highest power. A1 is the coefficient of the second highest power divided by coefficient of the highest power, equating coefficient of x power n minus 1 on both sides. See, on the left hand side it's minus of alpha 1 plus alpha 2 plus alpha n. On the right hand side it's a1 by a0. So equating that, this is what I get. Sum of the roots as negative of the coefficient of the second highest power divided by coefficient of the highest power. Then S2, which is sum of the product taking 2 at a time, would be minus 1 squared into a2 by a0, equating coefficient of x power n minus 2. Going this way, SR, sum of the product taking r at a time, would be minus 1 to power r AR by a0, equating coefficient of x power n minus r on both sides. How many terms would be there in this SR? NCR terms, right? Similarly, the product of the roots, which is sum taking all at a time, which is the last term, equating the constant term on both sides, minus 1 to power n, alpha 1, alpha 2, alpha 3, alpha n would be an by a0. So the product of the roots will turn out to be minus 1 to power n, an by a0, which is the constant term. An is the constant term in the polynomial, divided by a0, which is the coefficient of the highest power of x. That will give you the product of the roots. Yes or no? Do you all understand this? Seems okay, right? Now, see, if I have a polynomial like this, at cube plus bt squared plus ct plus d is a polynomial, pt. It's a polynomial of degree 3. How many roots will it have? 3 roots. What are the roots? t1, t2, t3. Right? What would be the sum of the roots? t1 plus t2 plus t3 would be negative of the coefficient of the second highest power divided by coefficient of the highest power. That means that's going to be minus b by a. If the second term didn't exist, then this will be 0. B will be 0. 0 into t squared. Say if it was 3t cube plus 4t plus d, then b will be 0 and the sum of the roots will be 0. Then sum of the product taking 2 at a time, t1 t2 plus t2 t3 plus t3 t1. This is sum of the product taking 2 at a time, right? That's going to be minus 1 squared. See, 2 at a time means minus 1 squared into C divided by A. Right? And the product of the roots T1, T2, T3 is going to be minus 1 cubed into D divided by A. That's the product of the roots. Sum of the product taking all at a time. Terms here would be 3C1, terms here would be 3C2, terms here would be 3C3. Just one term. Right? Yes or no? Right? Day 1 on parabola. This should suffice. Otherwise, there'll be a dielectric breakdown. Dielectric breakdown is a very commonly used term in physics, but